Okay, the topic of this set of notes is the continuous probability distributions. There's multiple different continuous distributions out there. We're going to focus primarily on the normal distribution. We'll start off with the uniform distribution just because it's an easy example to sort of explore first, but the main focus is going to be on the normal distribution. Now, it's a big difference between the topic we just previously covered, which was the discrete probability distribution, and the continuous distribution. Now remember, at the very beginning of a statistics course, one of the different classifications of data that you would normally cover is discrete data versus continuous data. And discrete data is countable, continuous data is only measurable. Okay, so with the discrete probability distributions, that was basically a list. You list every possible outcome of your experiment or your procedure, and this corresponding probability, usually given in the form of a 2-column T chart or maybe a bar graph. In this case, since continuous data takes on infinitely many values, we can't list them one by one. And listing doesn't even make sense with continuous data because if you choose one value at random, there's no well-defined next number, so we can't even write a partial list. Okay, so what we're going to do is use graphs. We're going to use continuous graphs instead of lists. So we list discrete outcomes, we graph continuous outcomes or continuous probability distributions. Now, in statistics, we call these graphs probability density curves. A curve is a graph. So this just means graph. Probability density curves. These are graphs. Okay, and we're gonna talk about how to use graphs to describe the distribution of probabilities corresponding to continuous random variables. Okay, so a probability density curve, again, it's just a graph of a continuous probability distribution function. So it can have any shape. The shape of the graph is not what makes it used for probability. What allows us to use a graph for probability is right here. It has to follow these two. It has to have these two characteristics. One, the total area under the curve, under the graph, must equal 1. And every point on the graph has to have a vertical height that is 0 or above, 0 or positive, so no negative y value. So basically, the total area is 1 and no negative y values. No negative y values. Okay, so here's an example. Here's an example of a probability density curve. It's a function that has no negative y values. There's no points down here. And the total area is equal to 1. And if your graph has meets these two criteria, then we could then there's a natural correspondence between the outcomes of an experiment or procedure with a continuous random variable and area. So basically, I want you to connect those two words, area and probability. Area and probability. If you're dealing with continuous data, and if you have a continuous probability distribution, then area is directly related to probability, and probability is directly related to area. So if, for example, we wanted to calculate the probability that we've already got an A and a B here. So let's say this X value here, we'll call that C, and this X value here, we'll call that D. If we want to calculate the probability that X falls between C and D, well, that's going to be equal to this area. between C and D. So probability, area. So to calculate probabilities, we're going to have to calculate areas. Now this is not a basic geometric shape. It's got a curve on the top, so we can't use any basic geometric formula. So we'll talk about using Excel to find those areas. All right, so again, we're with continuous data, since you have infinitely many possible values that the random variable could take on, the probability of any one individual singular event is always 0. So with continuous data, the probability of a specific outcome is always 0. So instead, we're going to only consider the probability of a range of values occurring. Okay, so what I mean by that is, what is the probability that, say, the next person to walk through the door is taller than 6 feet? So that's 6 feet or above. So let's use blue here. So the probability that x is greater than 6. Or what's the probability that the rainfall during the next month will be less than 3 centimeters? So what's the probability x is less than 3? And the only other option is probability x is bigger than, x is smaller than, or x is between two numbers. So the next fish caught will be between 3 and 5 pounds. So that's the probability x is bigger than 3 but less than 5. So these are the 3 scenarios, and these are the only 3 scenarios. Greater than, less than, or between. And this is really important because every single problem within this topic is one of these 3 types. There's no fourth option. Either x is greater than, x is less than, or x is between. Okay, just to recap the last few slides, continuous probability distributions are given as graphs, not as tables. And to calculate the probability, you calculate the area, either to the right of x, the area to the left of x, or the area between 2 x values. Okay, so we'll use Excel, and we'll talk about how to use Excel for each of these 3 scenarios. Okay. One thing that's worth pointing out is that when you have discrete data, or when you're working with a discrete random variable, the greater than and the greater than or equal to are not the same thing. So if you're rolling 2 dice, you could roll 2 dice and end up with a sum anywhere from 2 to 12. So a sum greater than 6 means 7, 8, 9, 10, 11, or 12. But a sum greater than or equal to 6 also includes the 6. So 6, 7, 8, 9, 10, 11, or 12. So in one case you have the 6, in the other case you don't. Now, with continuous data, the probability that x equals 6 is always 0. So you can ignore the equal to part. Okay, so now let's talk about one specific example of a continuous probability distribution, and that's the case of the uniform distribution, where every value is equally likely of occurring. So you have a continuous random variable, and every value is equally likely. So it should make sense that the graph is a horizontal line. No x values are more likely, no x values are less likely. So there's no part of the graph that's above another part of the graph. All right, so here's an example of a uniform distribution. It's just a horizontal line. You can't get any simpler than that. That's why I'm starting with the uniform distribution. Now, area of a rectangle is base times height. And the base here is 2, 123 to 125. And the height is 0.5. So 2 times 0.5 equals 1. So yes, this is a probability distribution, or this is a graph that can be used for a continuous probability distribution because the total area underneath the graph is equal to 1. And if we wanted to find the probability that a randomly selected voltage level is greater than 124.5 volts, we're looking for the probability that X is greater than 124.5. 124.5. And that's going to be, let's get rid of that. That's going to be this area, the area to the right of 124.5. So greater than this number. Okay, so, and this is fundamentally important for this and the next half dozen or so topics in statistics. The fact that with a continuous random variable, finding probability means finding area. Okay. So we're not going to do much with the uniform distribution. The big one, the really important type of distribution is the normal distribution. Now the word distribution, that's the shape of the graph. So all normal distributions will have more or less the same, no, not more, they will have the same shaped graph. The graph might be, one might be skinnier, one might be wider, one might be stretched or shifted, but they have the same general shape. Okay, so with the uniform distribution, with any distribution, there's going to be a mean and a standard deviation. We're not going to do much with this, but these are the formulas for the uniform distribution. But I'm gonna skip over to the normal distribution. So, if you've taken a course in algebra, whether or not you're comfortable or confident with algebra, just the concept of a graph. So we have linear graphs, straight lines, we have parabolas, things like this. Well, every x squared function will have the same general shape, a parabola. It might be down here, pointed down. It might be skinny up here. It might be wider like this, but they all have the same general shape. The normal distribution is just like any other function in algebra, except it's a little bit more complicated than what you might see. This is the formula for the, or this is the function. This is the normal distribution function. Now, if you were to graph this, it would look like this. We call this a symmetric bell-shaped graph, meaning most of the data is in here, close to the mean. And as you get farther away from the mean, either above or below, the likelihood of things happening gets less and less and less. We're never going to work with this formula. It's just there for... so you know where the graph is coming from, but we're never going to work directly with this formula. We're just going to work with the graph. Now, let's see. So sort of use a specific example for something that occurs with a normal distribution. Let's talk about height. So the average height of an adult male living in the U.S. is about 5'9". Now I'm rounding just so we don't need to use decimals and stuff like this, and with a standard deviation of 3 inches. It's probably closer to 2.9, but so what that means is, since the height of an adult male in the U.S. is normally distributed, that means the mean is 5'9". Now, it's not unusual to see someone who's 6 feet tall or 6'1". Those values are above average, but they're not very uncommon. Or 5'8", 5'7". These values close to the average are likely to happen. But how often do you see someone who's 7 feet tall? Well, that would be way over here. Or an adult male that's 4'9", that would be way over here. Very unlikely 4'9" or 7 feet tall. And so whether you're going above or below the mean, the farther you get away from that mean value, the less likely things are to happen. Okay, so that's in essence, that's what a normal distribution is. Okay? Since the graph is metric, the mean, the median, and the mode are equal to each other. And even if the graph doesn't go to infinity in both directions, theoretically we treat it like it does. Okay, so here's 4 different normal distributions. And what you'll see over here in this little legend, the blue graph has a mean of 0. The red graph has a mean of 0. The mustard colored graph has a mean of 0. The green graph is shifted over, it has a mean of -2. So they all have the same basic shape, and some of them are more tightly packed, meaning less variation. So you look at the variance of the blue one. The variance is 0.2. And you look at the variance of the mustard colored graph is 5. So higher variance means the data is more spread out. So you look at this normal distribution is very spread out. Okay, so the mean changes the location of the graph, and the standard deviation changes how skinny or how wide it is. Okay, and there's one graph here of significant importance, and that's the red one. So the red one has a mean of 0 and a standard deviation and variance of 1. That is a special case of the normal distribution. We call that the standard normal distribution. So the standard normal distribution in this one, it's blue. So the standard normal distribution has a mean of 0 and a standard deviation of 1. Okay. Either way, the area under the graph is always equal to 1. Otherwise, it would not be a probability density curve. It would just be a regular graph. Okay, we saw the empirical rule a few topics ago, and that says if your data is normally distributed. Now, it doesn't. We saw this when we covered probability before discrete probability distributions, because the empirical rule is not specific to continuous data. It applies to continuous or discrete data, as long as the data is normally distributed. And what it means is about 68% of the data will be within one standard deviation of the mean, or have a z-score between -1 and 1. about 95% of the data is within 2 standard deviations, and about 99.773% will be within 3 standard deviations. So, for example, suppose SAT scores roughly follow a normal distribution. Let's say the average SAT score is 500. The average math SAT score is 500 with a standard deviation of 50. That means if you go up 50 and down 50, not negative. Then what this previous slide is saying is that about 60, I'll just round it to 68, about 68 of all students' scores will be 68, about 68% of all students' scores will be within that range. And if we go out another standard deviation, so another 50 up and another 50 down, so that would be 400 to 600. Well, then about 95% of all students will have scores between 400 and 600. And then if we extend it another 50 up and another 50 down, that will catch 99.7% of all scores. Okay, so but this is just an estimation. We're going to be concerned more with exact values. For that, we're going to use Excel. We're not going to be referencing the empirical rule very often. All right, so there's various methods for calculating the area under a curve, above a value, below a value, or between two values. There's various statistical platforms and softwares. There's Excel, which we're going to be focusing on. You could use a method, maybe like a table of values that you pull off the internet or from a stats textbook. If you're using a table of values, we have to be able to use the same table for all the different data sets out there. So we can't have one table for inches and one for millimeters and one for pounds and one for years and one for dollars. With all these different units and different scales and different standard deviations, we have to have only one table that works for all these different sets. So what we do is we standardize the data. We change the data. We change the units. We convert the units from whatever they are into z-scores, number of standard deviations. And we talked about converting to z-scores in a previous lecture. So remember, each x value has its own z-score, and we could convert, and basically z-scores is just a shorter way or an abbreviated way of saying number of standard deviations. Okay, so let's see, here, I'll go back to that last slide in a second. Here's our formula for z-scores. We covered this a few topics back, but this is how we convert from inches into number of standard deviations, or dollars into number of standard deviations, or miles to number of standard deviations, and so on. So we have, if we're using Excel, we could do one of two things. To compute the probability of something happening, you could do one of two things. Convert your x values into z-scores. So that means to take a non-standard normal distribution and convert it into a standard normal distribution. So when you do that, you're changing the mean and the standard deviation into the values 0 and 1. 0 for the mean and 1, so that's down here, 0 for the mean and 1 for the standard deviation. Or you could keep the non-standard normal distribution because Excel has a built-in function for both. So there's a standard normal distribution function and there's a non-standard normal distribution function. They're almost the same, and we'll go through what how to apply each one of them. Okay, so on Excel, we talked about the 3 scenarios. The probability x is less than, let's say, some number c. The probability x is greater than some number c. And the probability that x is between 2 numbers c. Let's call them c. C as x is less than d. Okay. Now the function in Excel is norm, N-O-R-M, dot D-I-S-T. So normal distribution. And for, remember, the probability that something will be less than x is equal to the area to the left of x. And the probability that something will be greater than x equivalently is the area to the right of x. So this Excel function, this normal distribution function, gives you the area. Remember, area and probability are the same.